So this is a simple case of being able to solve for non-homogeneous. We're still talking about like constant coefficients and all those nice things. And um, this section will have a lot of special cases, or not. I don't know if you call them special cases, but they have little nuances when you're trying to solve for non-homogeneous differential equations. And the idea here is to be able to um, pick up on the little nuances and and then eventually be able to solve for them. What happens when you try to find a particular solution for a differential equation is that you 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 guess on what your solution is going to look like. And that guess is based on the right-hand side of your differential equation. And depending on the right-hand side of the differential equation, you're going to form your guess with some coefficients that you're going to solve for. And when you solve for those coefficients, then you have a particular solution. Okay? And this is one of those things where I could explain it a bunch of different ways, but really the best thing to do is to take a look at some examples. And we'll take a look at some examples, and then I highly encourage for you to practice, practice, and practice. So the idea is that if your right-hand side is just a constant, then you're going to have a constant for your guess for what the function is going to look like. If you have an x technically is a linear function, polynomial of first order, first degree. And so what we want to do is we want to replace the polynomials with as general a polynomial as possible. And if you have a linear polynomial, the general linear polynomial is mx plus b or ax plus b. And so you have two coefficients. If you have a quadratic, then your general polynomial is ax squared plus bx plus c. Again, even if your right-hand side, it has a second degree polynomial and there's some missing terms, like the linear term is missing in this case, you still want to get the most general polynomial as possible. Okay. Now we've seen already that sine and cosine kind of come in pairs, and it's dependent on having complex roots. And so your guess, if you have a sine or a cosine on the right-hand side, your guess will involve the pair of them, the sine and cosine, with the same angle. If you have an exponential, then it's just an exponential. If you have an exponential combined with a linear or a quadratic or any polynomial, then you have the most general polynomial times that exponential function. Exponential and one of the trig functions, the trig function comes in pairs, so that's automatically going to generate your other trig function. When I say trig function, I mean sine and cosine, because tangent and some of those other functions are a little bit more complicated, and we cannot find a particular solution based on this particular concept if you have a tangent. So we'll have to save that for another method. So an exponential times one of the sine or cosine functions will be the combination of the sine and cosine functions with that exponential. Again, any polynomial involved will generate a general polynomial times a cosine and times a sine. And so this is probably, it gets really bad with those polynomials because you generate more and more coefficients that you eventually have to solve for. And then if you have a polynomial, an exponential, and one of those sine or cosine functions, then you'll get the combination of all that. Okay. So these are your guesses, and you would pretend that your y sub p, your particular solution to the differential equation, is going to look like this. You're going to solve for the coefficients a, b, or c, or whatever, and then you're going to be able to get your particular solution. And then on top of that, you would to get the general solution, you would include that with your homogeneous solution. And so that's all that stuff is kind of based on the superposition principle. And again, it would make a lot more sense when we start doing examples. So I think we did an example last time, but let's start up a new example. It wasn't due yet, was it? Oh, it was? Oh, sorry. How come nobody said anything? Oh, okay. I'll extend it. All right, let's do some. So you guys should be experts at this already, if you did the homework. Yeah, it'd be good to know why. Well, let's do an example and see if we can come back to that idea, why we would pick that. So the process of finding a general solution to this would be to first solve for the corresponding homogeneous differential equation. So that's what we'll do. We'll start off by saying solve y double prime plus y prime minus 6y is equal to 0. And then once we get that, then we'll take a look at the particular solution. So in this case, our auxiliary equation is going to be m squared plus m minus 6 is equal to 0. So if we factor, we're going to get a 6 and a 2 and a 3. One of them is positive. Let's see. The m is plus 3 is positive. M minus 2. That adds up to 6, right? Or multiplies to 6. Adds up to positive 1. So m is equal to negative 3 and positive 2. And so you have y1 is equal to e to the negative 3x, and y2 is equal to e to the positive 2x. And so your solution for this, I think they call it y sub c or something. The y sub p is the one for the non-homogeneous. I would call it y sub h, but I remember that they don't do it like that. So they use something. C sub 1 e to the minus 3x plus c sub 2 e to the positive 2x. So that's your solution for the homogeneous differential equation. Now let's take a look at this non-homogeneous differential equation and try to solve for find a particular solution that they call y sub p that would satisfy this differential equation. And based on our table and our guesses, this is a linear differential equation, or this is a linear function. 2x is a linear function. And so the most general linear function that we should be able to come up with is ax plus b. And now the idea is that you're going to put this into the differential equation, so we need a couple of derivatives. y sub p prime is equal to a, and then y sub p double prime is equal to 0. If I took the derivatives correctly, and then we plug that in to our differential equation to see if we can solve for a and b. So y sub 0 is going to be, or y double prime is going to be 0. Y prime is going to be a, and y is ax plus b. And according to this differential equation, this is supposed to equal to the right-hand side, which is 2x. So this kind of gives you a glimpse of why you would probably want your form, or the form of your guess for your particular solution, to look like this, in general. And then when you put all this stuff together, let's see what we have here. We have minus 6a times x plus a minus 6b. If we combine the terms with an x and then combine the terms without the x, and if you remember kind of looking back at, we did something like this, or the format looks similar to this when we did partial fractions or something, where you would write out all the polynomials and then put zeros where the term isn't there, or something like that. So that you can set them equal to each other and then form your systems, or whatever system of equations. I think I have minus 6a is equal to 2, and a minus 6b is equal to 0. Is that right? I hope. So a is going to equal to negative 1/3. And then b, if a is equal to negative 1/3, b is going to equal to negative 1/18. Wow. 12? 12. Oh, this is a third, right? Yeah, 1/18. So your your particular solution is going to be equal to negative 1/3 x minus 1/18. And then you can double check, but this is exactly how we solve for this, but you should double check in case you made any like algebra errors by putting this into the differential equation again and making sure that you get the correct result. So this is our solution, a particular solution. Let's label this as a particular solution to our differential equation. And so now we have a general solution. And the general solution, remember, this is a second order differential equation. It should have a 2-parameter family, and we'll get that from the homogeneous part. So general solution is going to be y is equal to c1 e to the minus 3x plus c2 e to the 2x minus 1/3 x minus 1/18. And what you can do is check this by taking the derivative a couple of times and plugging it back into the original differential equation. So let's do that this one time only. So check, see if this actually does work. So I need a couple of derivatives. I'm going to come up with negative 3c1 e to the minus 3x plus 2c2 e to the 2x minus 1/3. And then the second derivative is positive 9c1 e to the minus 3x plus 4c2 e to the 2x. And then that's it. So let's drop that into the differential equation. So our y double prime is 9c1 e to the minus 3x plus 4c2 e to the 2x. And then we have plus y prime. So y prime is minus 3c1 e to the minus 3x plus 2c2 e to the 2x minus 1/3. Is that a plus or a minus? I think it's a minus. Minus 6 times y, which is the original or the solution that we found, c1 e to the minus 3x plus c2 e to the 2x minus 1/3 x minus 1/18. All right, so let's distribute some stuff. Let me combine this and then I'll distribute the 6. So we have 9 minus 3 is 6, c1 e to the minus 3x. 6 c2 e to the 2x minus 1/3, and then I'll distribute minus 6 c1 e to the minus 3x minus 6 c2 e to the 2x. Minus minus is a positive. This is going to be 2x, and this is going to be positive 1/3. So we can see a couple of things canceling out. And then all we have left is a 2x, which is what the right-hand side was. And so now we know that this is correct, and this is in fact our solution. Okay. Any questions? So had we just guessed that our general solution was just ax instead of ax plus b, we would have lost that constant along the way. That constant disappeared in our second derivative or in our first derivative. And so we want to make sure that we account for every minor detail that's involved, especially with the polynomials. Okay? All right, let's take a look at another problem. Any questions about this one? All right, let's do another problem. What are we going to do now? Should we do a sine and cosine one? Let's do number 8. So again, we start off with the homogeneous differential equation. So let's ignore the 2 or the cosine 2x for now and focus on our homogeneous differential equation. So 4y double prime minus 4y prime minus 3y is equal to 0. And then go to our auxiliary equation. Now, if you can factor that, that would be great. I don't think I could factor it off the top of my head. I suppose we can guess, right? 2 and 2, 3, 8, 12, 8 and 12, yeah. So 4m, m, so this gets 12, is that right? No. Did it work? No. Well, when all else fails, you could just do a quadratic formula. So we got negative b plus or minus b squared minus 4 times a. A is 4, b is 4ac, negative 3, all over 2a. So this is going to be positive. 16 plus 16, it'll be 4 under the square root, right? Did I do that right? 4 times 4 would be 16. This will be 8. And this is this 8? Yeah, this is 8. So 1/2 and, wait, negative 1/2 and positive what? 3/2. So it looks like we have a couple of exponential functions again. y1 is equal to e to the negative 1/2 x. And y2 is going to be equal to e to the positive 3/2 x. All right, so we'll deal with that later. We'll throw some constants in front and then put it all together. Let's get the particular solution now. So a particular solution looks like it's a cosine, so it should be a linear combination of the sine and cosine functions. And then from here, we need to take a couple of derivatives to put it into the function. So y sub p prime cosine negative 2a cosine, sine. And this is positive 2b cosine 2x. And then the second derivative will give us a cosine 2x. All right, then we get to insert those into the differential equation. So we got minus 4a cosine 2x minus 4b sine 2x. So that's our second derivative. Our first derivative is minus 2a sine 2x plus 2b cosine 2x. And then our y itself is just a cosine 2x plus b sine 2x. So if there's a sine 2x here on the left-hand side, we're going to set the coefficient of that to equal to 0. Let's take a look at all the cosines that we need to put together. So we have a negative 16a and a negative 3a, negative 19a, And then we have minus 8b. Did I do that correctly? So just the cosines, and then now I'll collect the coefficients of the sines. So let's start with the a, the sine. This is going to be positive 8a. And then the cosine, the b would be negative 16 minus 3. That's negative 19 again, right? So I want to set that to cosine 2x, which has a coefficient of 1, and then there's also this 0 times sine 2x, and so I can set up my system of linear equations, minus 19a plus or minus 8b equal to 1, and then 8a minus 19b is equal to 0. Whatever it is we need to do here. Set up a matrix. Set up a matrix, use Cramer's rule, or punch it into Wolfram alpha. That would be my guess. Well, somebody can get it faster. So solve. I got a system here. Got minus 19a minus 8b is equal to 1. And 8a minus 19b is equal to 0. Are you programmers? The double equal sign. If you accidentally put an equal sign, you get all screwed up. Ooh, look at this. Divided by 425. All right, so let's just copy the results here. So we have our solution. Which means your particular solution, y sub p is equal to minus 19 over 425 cosine 2x plus, I guess that's a minus also, minus 8 over 425 times sine 2x. Okay? And then to get our general solution, we just superposition it all together. Keep our y1 and y2. That's our fundamental solution. So we got our arbitrary constants, C1, e to the minus 1/2 x, plus C2, e to the 3/2 x. So that's the solution to the homogeneous differential equation. And then now the particular solution is minus 1 or minus 19, 425 cosine 2x minus 8 over 425 sine. Okay. Any questions? All right. You're ready for it to get weird? There's more. So this is manageable, right? So far? So far, so good. All right. See if we can get weird. Um, let's do a superposition example. Number 6. So the idea behind superposition, if you recall, is if you have a solution to one thing and then you have another solution, you can just add them up. So what we have here is a right-hand side that looks like it's of two different forms. And so when you have something like that, what you could do is you can find a particular solution for one of the terms and then find another particular solution for the other term and then just add them up. So that's the nice thing about superposition principles. And so let's do this, and I'll show you what I mean about adding them up when we get there. And again, we always start with the homogeneous differential equation. And then find the solutions. So we get our auxiliary equation. And is this factorable? 8 and 9, or 8? Okay. So can't factor. M is equal to minus b plus or minus the square root of b squared minus 16. Oh, you got the solution already? So equals, what is it? All right. So let's say we do this and we get our imaginary number. So we know that we're going to have, there's a real part to this, right? The 4 is a real part, so we need an e to the 4x. So y1 is equal to e to the 4x times cosine of 2x, and then y2 is equal to e to the 4x sine 2x. So if you haven't noticed, this is one of those things now where math is foundational and it builds on your previous knowledge, and so you have to be able to solve homogeneous differential equations to be able to solve for non-homogeneous. And if you're having an issue about where we got this solution, you should go back and take a look at the homogeneous differential equations and make sure you got that down. All right, we have our solution to the homogeneous portion. Now we're going to break this up into two particular solutions that we're going to find. Okay, so we're going to say this is going to be associated with y sub p sub 1. And that, since this is a quadratic, we're going to do a quadratic, general quadratic term, ax plus b, ax squared plus bx plus c. And then separately, we're going to consider y sub p2, which is going to be the solution for the second portion. And that general term, so we have an x times e to the x, so the x will generate a general linear term. And I could still use a and b because I'm going to do this separately. But if you're not feeling comfortable with this, you can go d and e because we're using a, b, and c's here. But we're going to actually treat these two problems separately. So I feel okay about just reusing or recycling a and b. All right. Yeah, that would suck. That doesn't happen. Ah, yeah. If only in our dreams, huh? It was tiring. I was helping out in the back. They got better. It was really bad. Not bad. It wasn't that good on Thursday night. And then Friday got better. Saturday. I think they peaked on Saturday. Sunday just went, okay. Hmm? Telling you, kids these days. All right. Let's work on the y sub p1, our first particular solution. Um, so we have our derivatives. Hopefully I did the derivatives correctly, and then we're gonna punch them all in. We got 2a for the first or the second derivative, and then the first derivative is 2ax plus b, and then our regular function multiplied by 20 is ax squared plus bx plus c. And then this is, since I'm only working with one of the terms right now, I'm just going to put that term here, 100x squared. All right, let's see if we can gather all the x's and the x squareds together. There's only one x squared here. So this is a 20ax squared. Now let's see if we can gather all the x terms together. So all the x terms together, there's a negative 16 times a and 20 positive 20b times x. And then now the constant terms. We have a 2a minus 8b plus 20c. Okay, so we have a 20a is a coefficient of x squared, 100 is a coefficient of x squared on the other side, so a is equal to 5. Is that right? 5? Put a box around that so we don't lose that. We got minus 16 times a, which we found out to be 5, plus 20b is supposed to be equal to 0. And 16 times 5 is 80. So 20b is equal to positive 80 on the other side. B must equal to 4. And then we got 2 times a, which we found to be 5, minus 8 times b, which we found to be 4, is equal to 20c. And that, oops, plus 20c. And that also should equal to 0. So we got 10 minus 32 negative 22. Is that right? So bring it over to the other side. We get positive 22. So C must equal to 11 over 10. 11 over 10. All right. So we have our particular solution, let's call it y. The first part of our particular solution is going to be 5x squared plus 4x plus 11 over 10. Okay. All right, now we got to deal with this other one where we have a product of two functions. So to find its derivatives, we need to use a product rule. Derivative of the first times the second plus the first times the derivative of the second. We can combine this to be ax plus a plus b times e to the x. So I just want to combine that so that when we take the derivative again, we can use the product rule just one time. So the second derivative, derivative of the first times the second plus the first times the derivative of the second. And again, we want to combine everything here so that it looks as simple as possible. So I think this is ax plus 2a plus b is equal to e to the x. Oops, times. What's equal? All right. So let's go ahead and drop that into our differential equation, except now we're only going to focus our right-hand side on that other term. So we have the second derivative. We got ax plus 2a plus b e to the x. This is y double prime. We have a minus 8y prime, and y prime was ax plus a plus b e to the x. And then we have 20 times y, which was ax plus b e to the x. And this is going to equal to negative 26x times e to the x. Okay, so they all have an e to the x, so we can just practically ignore the e to the x's. In fact, we could see if we could just cancel all that stuff out. So there's an e to the x, e to the x, e to the x. You factor that and cancel out with e to the x on the other side. So let's just deal with polynomials here. And then now let's gather. So these are all, they all only go as far as the linear terms. So let's find out the linear terms here. We got a minus 8a plus 20a. $13. Yeah, okay. Positive, right? 13a times x. Okay. So now the linear, the constant terms will have a's and b's. So let's gather the a's first. We got 2a minus 8a is negative 6a, negative 6 plus 20. No, there's no a there. Negative 6a. And then the b's. So there's a b, b minus 8 b negative 7 plus 20, 13 again. Okay, so I hope that takes care of everything. This is supposed to all equal to negative 26x, and you can put plus 0 there. Because you're going to set the coefficients of x equal to each other, and then the constant terms equal to whatever the constant term is. So 13a is equal to negative 26. Looks like a is going to be equal to negative 2. And if a is equal to negative 2, I have minus 6 times negative 2 plus 13b is equal to 0. That's 12. 13b is equal to negative 12, right? And b is equal to negative 12 over 13. So we have y sub p2 is equal to a. So remember the form of this is ax plus b times e to the x. So the form here is going to be a negative 2x minus 12 over 13 times e to the x. So that's your second particular solution. So your general particular solution, according to the superposition principle, which tells us that we can just add them all up together, is equal to the first particular solution, which is 5x squared plus 4x plus 11 tenths plus minus 2x minus 12 over 13 times e to the x. So this is your particular solution. And if you're interested in taking the first and second derivatives of this and putting it back to the original differential equation, it should work out. I'm not interested in doing that. And finally, the general solution would be the two fundamental solutions with a C1 and C2, and then add on the particular solution. So we have, this stuff for the e to the x, e to the 4x cosine 2x. So y is equal to C1, e to, was it 2? 4, and then cosine 2x. Plus C2, e to the 4x sine 2x, plus all this big mess that we just found, 5x squared plus 4x plus 11 tenths plus negative 2x minus 12 over 13 e to the x. Hopefully. Should we try? I'm going to call on some help for this one. So let's say our y of x is equal to some constant times e raised to the 4x times cosine 2x. Cosine integral, what? Plus C2, I'm just going to copy here, a different constant, and this is sine. Now we got the polynomial 5x squared. Oops, that's not squared. 5x squared plus 4x plus 11 divided by 10 plus we get a minus 2x minus 12 divided by 13 e to the x power. Okay. Oops. So what do we want? We want y double prime. What's a plus, minus? What was the differential equation again? Minus 8 times y prime plus 20 times y of x. Should ask it to simplify. Does that work? 2 times 50 is 100, x squared. 2 times 13 is negative 26. Negative 2 times 13, negative 226, x times e to the x. Works? This is kind of silly. What is it? Negative 26 times x times e to the x plus oh, it doesn't say if it's true or not. Yeah. Well, I think it's going to be more complicated. Let's see. It's equal. All right, so it worked out. Let's see. Let's ask it to solve this. I have to clear stuff. Oh, it has to be equals. What was it again? This stuff. I have to clear. Here's our solution according to Mathematica. It's equal to 1. All right, yeah, that's more confusing. So, any case, we found the solution, we checked it, and it did work. So, I think that's good. Okay. Questions? So this thing, the constant, this thing with another constant, this is your particular solution. So this is apparently equal to 1 if they simplify it. So it's just this thing with a negative in front. Anywho. Well, here we found two portions of our particular solution, and in general, this particular solution would be the sum of those. Oh, yeah. So basically, if you have a polynomial, then you want to find the most general polynomial. If you have an exponential, then it's just the exponential. If you have either sine or cosine of the same angle or both, then it's a combination of those sines and cosines. Um, and then if the sines and cosines are multiplied by a polynomial, then general polynomial. And then if it's multiplied by the exponential, it's exponential times that. And then if it's multiplied by a polynomial, an exponential, and the trig function, then it's a combination of all those. So it's one of those things where the more you do it, the less it's going to have to be memorized. But then again, you don't have to memorize things because you guys will have a sheet of notes on the test. You might have to memorize it for a quiz. I don't know. But in the test situation, you'll have a table like this, or you should come up with a table like this or something similar. You get whatever, you get a sheet of notes on your test, right? So put whatever you want. If you don't want to put the table, fine. If you have it memorized, then save that room for something else. Because of the way our sine and cosine functions for the homogeneous differential equation, when we get the imaginary complex numbers, you have to include both the sine and the cosine to kind of work together. So in doing that, you want to be able to compensate. Yeah, we're getting there. It is in this section. We'll get in. All right, let's do number 12. Should have done number 10 instead of number 6. That was. I think I'm ready now. I suppose I should ask you. Are you ready? Oh yeah, it just gets weirder. This one, it looks so innocent. Let's see how innocent it is. Um, so for this one, same process. We start with the homogeneous portion, and then we find a particular solution. So the homogeneous portion is the second derivative minus 16 times the original function is equal to 0. Auxiliary equation, m squared minus 16 is equal to 0. So that's plus and minus 4. And then we have y1 is equal to e to the negative 4x. Y2 is equal to e to the 4x. Okay, simple enough. Now, when we look at the particular solution and the form for the particular solution, we notice, by the way, all the superposition principle relies on your functions, your fundamental functions, your particular solutions to be linearly independent from each other. Otherwise, they repeat, and if they repeat, then you're saying the same thing, and then that the whole idea of the fundamental solutions being linearly independent from other functions is going to get messed up. So if I look at the particular solution, I would think that it would just be a times e to the 4x, right? Unfortunately, we have e to the 4x as a solution to the homogeneous differential equation already. So we cannot use this because if we find a solution for this, then it's going to just be linearly independent with a homogeneous differential equation. So linearly dependent with the homogeneous. So what we're going to do is we're going to change our y particular to tack on a linear term. You know how we find a solution to our homogeneous differential equation, and we say the solutions repeat. So to keep it from being linearly dependent, we make one multiplied by x, right? So it's going to be the same kind of concept, except you're going to multiply by, you know, a general linear term. We can't use this because it is linearly dependent on a homogeneous solution. You guys can try it and see what happens. Okay, so now we have this, and we got second derivatives. I think we can do this in 5 minutes. So it's a product, derivative of the first times the second, plus the first times derivative of the second. And again, this is something where I'd probably want to put everything together and simplify. You know, when you take derivatives, you ask your teacher, do you have to simplify it? And the teacher says, no, you don't have to simplify it. Well, if you need to take the derivative again, you probably want to simplify it. So I have a 4ax plus a plus 4b e to the 4x, just so I can have a two-term or two-factor derivative again. So it's derivative of the first times the second plus the first times the derivative of the second. And then again, I probably want to simplify this because I'm going to end up putting this back into the differential equation. And so I want the most simplest term as I can get. So I have 16 ax as my linear term. And then I have a 4a, that's 8a, and then a 16b. Okay, so that's my second derivative. Goes back into the differential equation. Differential equation, fortunately, is just two terms. That's a second derivative, 16ax plus 8a plus 16b e to the 4x minus 16 times ax plus b e to the 4x, and this is supposed to equal to 2 e to the 4x. So I'll again knock out the e to the 4x, and then I will look for the linear terms and the constants. So I have a 16a, negative 16a, that disappears, right? So the linear term is gone. And the 16b also disappears. So we got 8a is equal to a constant 2, so a must equal to 4. 1/4. So that's it. That's my linear term, or my particular solution. Y sub p is equal to 1/4 x e to the 4x. Okay? Something wrong? Did I do something wrong? All right. So now that we have that, we can string them up, and all these, the fundamental solution as well as the particular solution, are all linearly independent. And so that should work out just fine. General solution, y is equal to c1 e to the minus 4x plus c2 e to the positive 4x. plus 1/4 x e to the positive 4x, all linearly independent, superpositioned, tapped on, added together, answer. Questions? You're gonna do it this way if your right-hand side is linearly dependent with one of your homogeneous solutions. Yeah. Yes. So this could be a spring problem. So the right-hand side describes some motion of the spring, and then the left-hand side could be some external motor that you're doing to the spring. So maybe you're applying a special motion to the spring, a special motor that's of this form. Michael. The left-hand side is a spring, and then the right-hand side is a motor that pushes the spring. Our solution tells us that this is how the motion of the spring is going to look like in the long run. Sure. Not right now. But yeah, I can set up a graph.